Welcome everyone to the fourth and last talk of today. And I'm happy to introduce Vince Vatter from the University of Florida. And he will tell us about growth rates of grids and merges of permutation classes.
Thank you very much. Thank you for inviting me. It's an honor to speak here. Of course, Daron was my advisor. Although a lot of this work is more closely related to Amitai's work. So I've got a couple different things in here that I want to tell you about. First, although Tufik already told us about permutation patterns, I just want to emphasize that I'm thinking about this really kind of pictorially. So I'm thinking about the permutations as being functions from the integers 1 through n to the integers 1 through n, and then I'm plotting those functions. Okay, and if we think about a subpermutation as just select some of those dots and reduce their values, standardize their values. Okay, so here's an example. Now, this is a partial order on the set of all finite permutations, and I'm going to call a downset in this order a permutation class, or just a class. And so, a permutation class looks like, this sort of thing in the post set of all permutations. And you can specify them all by what patterns they avoid. Okay, and we could even make it unique by saying it's the minimal patterns that they avoid. That doesn't have to be a finite list, but it's some list of patterns that you avoid. Okay, and if we want to think about this as the post set, it gets complicated very quickly. If we want to avoid 2, 3, 1, well, we would cross that 2, 3, 1 and everything it contains. Okay, so this is the very basics. Now let's look at a couple just easy examples of classes. So one would be the layered permutations. And I've just drawn an example here. You just take decreasing segments and you stack them on top of each other. Okay, so that's what the layered permutations are. It's easy to see that you can describe a layered permutation just by the composition of its layer lengths. So they'll be in bijection with compositions of n. So we know that there's 2 to the n minus 1 of length n. And if you think a little bit more, these can be defined by avoiding the patterns 2, 3, 1 and 3, 1, 2. Okay, 2 more examples. The next one would be the 2, 3, 1 avoiding permutations. These were famously studied by Knuth in The Art of Computer Programming, where he showed that these are the ones that can be sorted by a single stack. Now, if we want to count these, we look at the position of the largest entry, and we see that the things to the left have to be smaller than the things to the right. And they both have to avoid 2, 3, 1 themselves, and that's sufficient to make a 2, 3, 1 avoiding permutation. And you just write that down, that's the Cato n recurrence. And, very roughly, there are 4 to the n of length n. Okay, ignoring the pi and everything. An even simpler example, what if we take the layered permutations from before and we also avoid 3, 2, 1? Then our decreasing segments can only be size 1 or 2. Okay, we see immediately we're getting the Fibonacci numbers. Okay, compositions of n into parts of size 1 and 2. So it's about 1.62 to the n, the golden ratio. Okay, so those are the 3 really basic examples. That's the kind of thing I want to talk about today. Instead of, Tufik talked about this exact enumeration of permutation classes. If you think that's too hard, then you might want to try asymptotic enumeration instead. Okay, so I'm just going to look at, they grow like constant to the n. What's that constant? Okay, now, I'm sorry, Daron, for writing infinity in this slide, and I'm sorry for taking a limb soup. I'm not sure. I'm never sure if I'm allowed to do that.
You are forgiven today.
Okay. Do the real numbers have the least upper bound property today, or? Anyway, so this is the quantity I'm interested in, is these growth rates. Just asking, they grow like constant to the n. What's the constant? And Cyril asks, why should they behave like constant to the n? Well, the Stanley-Wolf conjecture says that this limb soup is finite for all the classes. Okay, it might be 0 or it might be 1, but it's going to be finite. Let me just point out, because there's so many great enumerators in this audience, I mentioned a few questions throughout this talk. One of them that I wish someone would settle is this. Except when Facquet's lemma makes this trivial, we don't know if we can replace that limb soup with a limit. Okay? By Facquet's lemma making it trivial, I mean if the class is super multiplicative, so the number of permutations of length n plus m is at least the product of the number of length n times the number of length m. If that holds, then Facquet's lemma says that this limit exists. If that doesn't hold, and it doesn't necessarily hold for all permutation classes, if that doesn't hold, then we don't know if that's a limit. So we have no counterexamples, but we don't know if it is. Okay. Now, here are the examples we've seen. The layered permutations, your growth rate is 2. 2, 3, 1 avoiders, it's 4. And then Fibonacci class, of course, the growth rate is the golden ratio. This is long and difficult paper of Amitai from 1981 called Asymptotic Values for Degrees Associated with Strips of Young Diagrams. Now, one of the things she does in there is the asymptotic enumeration of standard Young tableau of given shapes. One of the implications of that, although I don't even know that this is stated in that paper, but it's an implication of that. If you avoid a monotone pattern of length k, the growth rate of that class will be k minus 1 squared. Okay, now, I should say I'm calling this the theorem from that paper, and it's just one of the many implications of that paper. The easy part of this is the upper bound. It's at most that value. One way to see this is if you avoid a monotone pattern, let's say you avoid this k minus 1 ... 2 1, then the entries of your permutation can be partitioned into k minus 1 increasing subsequences. Now, if you do that partitioning and then you record from left to right which subsequence each of the points was in, and you record it from bottom to top, then you can recover the permutation from those two words you form. So it's not hard to see that the number of these permutations is at most k minus 1 squared to the n. A question that's bugged me for a long time is there an elementary proof of the other inequality? Okay.
Vince?
Yes.
Have you encountered examples of classes where you can have this limit to be non-algebraic?
We'll get to that in a second. Let me say something about that in a second, okay?
Okay.
The short answer is yes, but it's probably not the question you wanted to ask, okay? So this is a question I want you to think about. I don't have a good answer for this. I will give you an answer that I think is slightly easier to me. But if anyone has any thoughts about an elementary proof of this inequality, please send me an email or let me know in the chat or tell me after my talk, okay?
When do you mean a combinatorial, purely combinatorial proof or injective proof? What do you mean by elementary?
I don't care how you do it. I would just like it to be easy.
So in some sense, Regev's theorem is elementary. It's beautiful. Okay.
We can disagree about that.
But it's not easy. But it's not easy.
Yes. I want something, in a page, if I could.
But this is an asymptotic result. So for small n, is it true?
I've never checked to see if it's
Okay.
true for small
Shame on
n.
you. Okay.
Oh, well, I mean, sorry. So it can't be true for all n. Because that k minus 1 squared to the n will be too big.
Okay, so it'll be some cutoff. So maybe it's true eventually.
Yes, that would be,
Go ahead.
yes.
Yeah.
Okay, so I wanted to talk about this result, but while we're talking about growth rates, I can't help but tell you a little bit about the number line of growth rates. Because, even though Daron was my advisor and he got me into automatic enumeration, it was really a 2003 paper of Kaiser and Klazar that got me into what most of my work on permutations has been since then, which is that they look at the family of all permutation classes and look at all the possible growth rates. What does that set look like? And so they characterized it up to 2. It goes from 0 to 1. It's actually fairly easy to see there's nothing in between 0 and 1. Then it jumps up to the golden ratio. And then between the golden ratio and 2, you're just getting these things that come from, there's a million names for them, but maybe generalized Fibonacci numbers. Okay, they're all from that denominator that you can see kind of where that's coming in. And they accumulate it too. Okay, so since then we've filled in quite a bit of this number line. I extended the list to 2.2. And again, Daron, I'm sorry, you might have to cover your ears for a couple slides here. That's the point where there are uncountably many classes, if you believe in that sort of thing.
So it's completely fictional, okay, meaningless. But it's still maybe nice.
Yes.
Okay.
Just Daron, it's only going to be a couple minutes of meaninglessness. So.
Well, there might be still something that a finitary person would accept if you can show, for example, that there are numbers in this class that are not computable, for example. Can you do that sort of thing?
I have not thought about that sort of thing. Okay, then in another paper around the same time, building on work of Michael Albert and Steve Linton, I showed that starting at 2.48, you can get every real number as the growth rate of some class. So we had that question earlier, are all these numbers algebraic? If we're going to allow that the basis, the set of patterns you avoid to be anything, then we're going to get all real numbers. So clearly we're going to get non-algebraic things.
This is something, so to speak, constructive. I mean, you can fine-tune it algorithmically to make it, you could sort of introduce more forbidden patterns as needed to make it smaller.
It's as constructive as the real numbers are constructive.
Exactly.
Yeah. There's a mechanism for doing it. Yeah. Okay. Then in 2018, David Bevan, who is Daron's great-grand student, lowered that 2.48 to 2.36. So from 2.36 on, we can get all the real numbers. Working with my student, Jay Pantone, Daron's grand student, very recently, we extended the list up to 2.3, which is the point where, if you believe in it, there are uncountably many growth rates. Before I said there were uncountably many classes, but there were only countably many growth rates before. Okay, and so I just want to leave this number line with saying we've got this little gap of 0.06 where we still don't know what's going on. Okay, so that's the story about the set of all growth rates.
Are there gaps in the neighborhood where you've got countably many growth rates after 2? Are there still gaps, or is the set dense?
We don't know what this looks like. I believe it's going to be. I believe it's not going to be dense. Okay, if I had to guess. But yes, this is a mystery here. Now let me move on to. I wanted to get back to this Amitai result. So before we were just talking about arbitrary permutation classes, they can avoid as many permutations as you want. What if we just avoid a single pattern? Well, we already said that if you avoid 2, 3, 1, you're counted by the Catalan numbers. Your growth rate is 4. It's a famous old result that if you avoid 3, 2, 1, it's also the Catalan numbers. So your growth rate is also 4. If you avoid 4, 3, 2, 1, your growth rate is 3 squared, or 9. My colleague Miklos Bóna proves that if you avoid 1, 3, 4, 2, your growth rate is 8. There's also some work by Julian West and Stankova and others saying that for all the other patterns of length 4, you're actually one of these 3, and the third one, avoiding 1, 3, 2, 4, is still unknown. Okay, but the guess seems to be around 11.6. Okay, and I guess I should definitely mention Miklos established his result by counting that class. I'm citing Amitai for the growth rate of the 4, 3, 2, 1 avoiders, but of course Ira Gessel was the one who counted those. Now I want to talk about grid classes. These are difficult to define formally. So I'm just going to go slightly informally with it's defined by a matrix, and in the cells of the matrix, I'm going to put permutation classes themselves. And I want, and my grid class is all those permutations that I can subdivide their plot so that in each cell of the plot, I get a member of the class that the matrix is specifying. Okay, so there's an example matrix on the right. What would a member of that class look like? Here's a member. I've subdivided its plot into a 3 by 3 cell, and you can check that in every cell, the points in the permutation lie in the class specified by the matrix. Okay, which in this case just means some of them avoid 2, 1, some avoid 3, 2, 1, and some are empty. Okay, a notable non-member of the class that I've drawn on the right is 4, 3, 2, 1. It's not there, and the reason you can see it is the 4, 3, 2, 1 couldn't sit in any of the single cells, and if you think about partitioning it among 2 or more cells, you'd either violate the avoiding 3, 2, 1 condition or violate the avoiding 2, 1 condition. Okay, so that's just an example of a grid class. Now, David Bevan, I should say there are various flavors of grid classes. They're geometric, they're monotone, they're generalized. This one is the generalized one. So David Bevan proved a theorem that gave the growth rates of monotone grid classes. And building on that, Michael Albert and I extended his theorem to generalized grid classes and gave a sort of a linear algebra Lagrange multiplier proof of it. And our result says, if you define a matrix gamma by putting in each cell of gamma the square root of the growth rate of the class in that cell, then the growth rate of your grid class is the largest eigenvalue of gamma transpose times gamma. Now, I didn't write this in here. I should definitely say before anyone calls me out on it that you need to make a caveat about this. For this to be true, all of these growth rates have to actually be limits, not just lim sups. Okay. Now, again, we don't know of a case where the growth rate isn't the limit, but it has to be for this. Okay. And actually, when you dig into the proof, you're getting the largest eigenvalue of that matrix because it's the square of the largest singular value of gamma. Okay, and the proof of this consists of a singular value decomposition of that matrix gamma. Okay, so
Vince, does the matrix have to be a square or not necessarily?
No, it doesn't.
Because the definition doesn't require it. It doesn't.
Yeah, that's why it's actually proved using singular values. But yeah, when you take gamma transpose times gamma, you're always going to get a square matrix and that will have eigenvalues. Okay, so in our example, you just write the growth rates in your matrix gamma. You take gamma transpose times gamma. You'd compute the eigenvalue. You'd get 7.34 as the growth rate of that grid class. Okay.
Curiosity, is a grid class a class as a rule?
Yeah, it's a class because each of the cells we insist is a class. So when you delete points from the grid class, you stay in the grid class. Okay, so this 7.34, remember we said that 4321 is not in this grid class. So this grid class consists entirely of 4321 avoiders. So the 7.34 growth rate of this class is a lower bound on the growth rate of the 4321 avoiders. Now we know the answer there is 9, so 7.34 isn't very impressive, but maybe we could make this example bigger. Okay, so let's think about the 4321 avoiders. What if we took this, we call this thing a staircase. What if we did this particular staircase? Well, you can see, again, that 4321 is not contained in that grid class. Because there's just no way to split its points, so that its points don't all lie in the same cell, and so it satisfies the avoidance condition. Well, then you look at gamma transpose times gamma. It's going to have 5s on the diagonal and 2s on the off diagonals. And so it's a tridiagonal Toeplitz matrix, and people have established formulas for eigenvalues of tridiagonal Toeplitz matrices. And if you do this particular example, and you take a T by T matrix of this form, so a T by T grid class of this form, your growth rate will be 5 plus 4 times cosine of 1 over T plus 1. Now, of course, in the limit, as T goes to infinity, that goes to 9. So that gives us a lower bound on the growth rate of the 4321 avoiders of 9, which is the correct answer. Okay. Well, this generalizes in the obvious way to give you the lower bound in the result we started with. Okay. Now, at the beginning of my talk, I asked for an elementary proof of this. I still don't think this is an elementary proof of that, but it's a proof that I understand quite well, obviously. I would still like an actual elementary proof of this bound. Okay. I want to talk about another use of these staircases. So with Michael Albert and J. Pantone, we generalized this construction, and we were thinking about merges of classes. So take your two favorite permutation classes, and their merge is all the permutations where the entries can be partitioned into a member of one class and a member of another class, of the other class. So we can think about it as coloring all the entries red or blue so that the red points are members of C and the blue points are members of D, and every point got one or the other color. Okay. Well, I'm going to use this circle dot to denote the merge. If you look at the permutations in the merge, okay, so you take a permutation of length n in the merge. The upper bound, the easy upper bound I put here, is that you choose how many of your points were red, except you want to choose them by, you want to choose which values are red and which positions are red. Okay, and then you choose the permutation formed by the red points, and then you choose the permutation formed by the blue points. And this gives you this upper bound where the sum, you take a sum over how many points were red and choose that number squared times the number of permutations in the two classes. Now, if you play with that with that formula in the binomial theorem, you'll see that it's approximately the square of the sum of the square roots of the growth rates of the classes. Okay, and you can make this all rigorous with, some epsilons. So that is your easy upper bound on the growth rate of merges. And I'll point out that what we did earlier, what I said earlier is we can view the 4 3 2 1 avoiders as the merge of 3 2 1 avoiders with 2 1 avoiders. This is we said you can partition those permutations into, in this case, into 3 increasing subsequences. Take 2 of your increasing subsequences to be a 3 2 1 avoider and the other to be your 2 1 avoider. Our result about staircases says that this easy upper bound is actually the truth if this staircase, where if C's along the diagonals and D's on the subdiagonal, is contained in the merge. And the reason is you can just use that theorem, form the gamma T times gamma, use the formula for the eigenvalues of a tridiagonal Toeplitz matrix, and you get that square of the sum of the square roots. Okay. The easy upper bound is also the truth if this more complicated thing is contained in your merge. Okay, here the C's are along the diagonal and the D's are kind of along the anti-diagonal. I guess there's 2 lines of D's. Okay. Now, why am I sure, the way I presented these, they just look like two constructions. Who would care about these? The point is that frequently these are contained in the merges. So in particular, if C and D are both defined by avoiding a single pattern, then one of these 2 will always be contained in the merge. So if C and D are defined by avoiding a single pattern, then the growth rate of their merge is equal to that easy upper bound, always. Another way you can use these results is to rederive some results of Miklos-Bóna. So he showed that the 5, 4, 2, and 3 avoiders can be expressed as the merge of the 2, 1 avoiders with the 4, 2, 1, 3 avoiders. So by our result with the staircases, that growth rate is going to be equal to, here it's 9 plus 4 times the square root of 2. Okay. This at the time when Miklos did this, for avoiding a single pattern, this was the first example of a non-integer growth rate. Okay. 2007, he generalized it. Yes.
What does this say about avoiding k minus 1 up to 1 in particular?
Oh, if you avoid a monotone pattern, these results give you that k minus 1 squared.
Okay.
Does that answer the question?
Yes.
Okay. So Miklos generalized this result a couple years later. As long as we're avoiding a pattern of this form I've shown on the left, then we can break it up like this. And indeed, that's implied by the staircase construction. Okay. I want to conclude with one final question. Is this always the growth rate of a merge of 2 classes? Okay, we don't have a counterexample. Again, let me repeat that the upper bound comes just from playing with the binomial theorem. In the cases I've shown, the lower bound comes from these staircase constructions. But we don't have an example where this is not the case. Okay. And happy birthday to Amatai and Dara. So thank you.
Thank you very much, Vince.
I have a comment about an elementary proof of at the beginning. Amitai did give an elementary proof. All the components are elementary. The Robinson-Sensen-Knuth algorithm, or Robinson-Sensen, it's enough, is very elementary. It's a beautiful combinatorial result. It's a bijection. So this implies that the number of permutation avoiding 1, 2, k is the number of pairs of Young tableau with at most k rows. The Hooke length formula, another very elementary result that can be easily proved by induction. It's in Knuth. It's an exercise using Lagrange interpolation, and I have some proofs. And there's a beautiful bijective proof due to Franz Blau and myself, and also by Paquet Hall. So the Hooke length formula is also an elementary result. So Regev combines them, and then you get a beautiful multisum that using symbolic asymptotic enumeration, you can do everything finitistic, converges to the Selberg integral, for which is also a beautiful elementary proof, in particular using the so-called WZ theory. So all the components are elementary. So Vince's problem has already been solved. Thank you.
But maybe you couldn't fit that all in one page, right?
Maybe not. Okay.
To Shalosh, all of mathematics is elementary, I think, right, Duran? All of human
Maybe.
mathematics is elementary.
Yeah.
So perhaps I should have asked for a more elementary proof.
Okay. And also your unspeakable thing about uncountable, I think it can be made sense of if you try hard enough to make it nice. Okay.
Maybe it should be noted that I wasn't present. In the permutation patterns, maybe it was in Reykjavik, I don't remember. Right after that, Stanley-Wilf conjecture was solved, and people asked, maybe there isn't so nice structure as growth of PI algebras as Beryl, Amit Regev theorem. So all this line was motivated by the Beryl Regev, which a special case is the force. Also, I don't know if Richard is in presence, he was before, he told me at the beginning that the Stanley-Wilf conjecture was motivated by the Beryl Regev paper. So Beryl Regev essentially pushed the permutation patterns. I don't know if he is aware of this, but this field in mathematics was pushed forward by Amit.
Good point.
Vince?
Yes?
If there is going to be, I want this to be true, but if there is going to be a counterexample, where would you look?
Oh, I'm not really sure. So if you look at our paper, we give some speculation about where you might want to look. The thing is, you have to defeat those you have to make it so the staircase constructions don't give you the lower bound. And we actually spend a short section at the end of our paper giving an example where we say you might want to look at this because this isn't implied by our results. This case isn't implied by our results. I know that J. Pantone has looked at that case, and still the conjecture is true there. So I guess you have to try harder to find a counterexample. I mean, it may be true that this is. I mean, it may be that this is true, and actually, this has a fairly elementary proof, and maybe that's the nicest proof for avoiding a monotone pattern.
So Vince, I have a question. So in fact, you have an algorithm to compute possibly the row given by brute force. You can compute the growth rate. You can compute a number of digits of it. So it seems with this approach that all of them should be computable numbers. But we know that there is only a countable number of computable numbers. So which means that something is not working with this approach. So where is the bug possibly? Do you know?
if I understand correctly, you're saying that if the growth rates come from grid classes, then they're going to be computable?
Or even the previous example that you gave with the full continuity of real numbers. So by brute force, you can compute the number of permutations of a huge size, and then you can approximate the growth rate, taking the power 1/n and so on. And therefore, it should mean that those numbers are computable. Now, for sure, I see possibly where could be the bug. The bug could be that it could be the case that possibly you have infinite number of forbidden patterns. And this possibly is the way to encode this infinite list of forbidden patterns could possibly be tricky. So it could be one of the possible objections to this bug, paradox, if you want. Did you consider more of this? Another stuff could be more interesting. It could be that to get a very precise number of digits, you need more information on the next asymptotic term to get the error terms. And therefore, it would mean that there are some classes for which there is an accumulation of singularities going next to the growth rate. And then we won't be able to get the right possibly the right. So it should be one of the two possibilities. I'm not sure which one, or possibly both of them. So did you consider this question, this paradox?
No, I haven't considered that myself. I mean, I think someone like Jay Pantone would be a great person to ask that question to. So.
Vince, it seems that the square root of a growth rate behaves nicely under, at least here in merges, it's sub-additive and conjecturally additive. Are there other contexts where the square root of the growth rate is nicely behaved?
Yeah, I'm not aware of other contexts where it's where the square root naturally shows up, except that I guess everything in this talk, it was the square root of the growth rate was more natural, even for amortized result.
Yeah, it's K-1. Yeah. Other comments, questions? Okay, if not, let's thank again Vince and all the speakers of today and all the attentive listeners. And we'll meet again tomorrow, same time as today. Thank you, everyone.